there are several different separation properties for topological spaces, each of which is some way to measure the extent to which points or closed sets in the space can be separated by neighborhoods that contain them. The one that we are most familiar with so far is the Hausdorff property, and that says that for any pair of distinct points x and y in our space, there exist disjoint neighborhoods u and v of those 2 points. And we proved way back in chapter 1 that in a Hausdorff space, every single point subset of x is closed. So points are closed sets. Now, a little bit of a stronger property is x being regular. And in a regular space, just like in a Hausdorff space, 1 point sets are closed. But then this next one is a little bit more stringent than what we had before. So this time, for any point and for any closed set, potentially larger than a point that does not contain A, there exist disjoint open sets U and V such that A is in U and B is in V. Okay, so we're requiring ourselves to be able to separate not just points, but a point and any closed set. And a third separation property is normality. X is normal if, again, 1 point sets are closed. And 2, for every pair of disjoint closed sets A and B in X, there exist disjoint open sets U and V, which respectively contain them. Okay, so now we're not just allowing one of the sets to be something bigger than a point, but we're allowing both of them to be any closed set. All right, so in general, normal implies regular, and regular implies Hausdorff. And it turns out that it is possible for a space to be Hausdorff and not regular, and it is possible for a space to be regular and not normal. Okay, but that situation doesn't happen for nice spaces, in particular for compact spaces. In exercise 7.9, we're going to prove that if X is compact and it's Hausdorff, then it's automatically, well, first we'll show that it's regular, and then we'll show that it's normal. Okay, so for compact spaces, these 3 separation properties are actually equivalent. You can compare what we do here to exercise 5.23, where we showed that a metric space is normal, which is sort of a, yeah, okay, I'll leave it at that. So assume that we have a compact space, which is also Hausdorff. Then first of all, we know by theorem 1.19 that 1 point subsets of X are closed in X. And so it just remains to show sort of the second half of the regularity and normality properties. So let's prove that X is regular. Suppose we have a point A in X and a closed subset B of X that does not contain the point A. Well, since X is Hausdorff, if you take any point B in this set, capital B, you can look at those points A and B and find disjoint open sets. We're going to call them U sub B and V sub B here, such that A is in U sub B and B is in V sub B. And the reason I'm putting a B subscript on both of those is that A is just a fixed point here, but I'm letting this B vary all over the set B. Okay, so for every different location of this point B, I might get a different U sub B and a different V sub B. But what I know is that the collection of all the V sub B's that you get that way are an open cover for this set capital B, because every point in this set B is contained in at least one of them. All right. Well, if we have an open cover, then that's a good time to use compactness. So because B is a closed set of a compact space X, B is also compact by theorem 7.7, so there exists a finite subcover, which I'll write like this, which are basically the open sets that came from some finite list of points B1 through Bn. Now I'm going to, remember I'm trying to find sort of open sets U and V which separate the point A from the set B, and my set U containing A is just going to be the intersection of the UBIs corresponding to the VBIs in my list here, and my set V containing B is going to be the union of these VBIs. Okay. While a finite intersection, finite union of open sets are both open, so U and V are open sets, and all of the UBIs contain A, therefore their intersection does as well, so A is in U. And well, we just said that these VBIs form a cover of the set B, and so B is certainly in the union of them. B is in V. And well, it remains to show that these sets U and V are disjoint. Imagine we had an element in both of them. Okay. Because it's in the union of the VBIs, it's in at least one of them, some VBI, but then it's in all the UBIs, right? So it would have to be in that particular UBI and that VBI, but we know that those are disjoint, okay, from the Hausdorff property. So any element would have to be in the empty set. It means it can't exist, so U and V are indeed disjoint, proving that X is regular. All right, well, we've let one of our spaces be an arbitrary closed set. Now we're going to let both of them be, to prove that X is normal. So suppose we do have disjoint closed sets A and B in our space X, and well, we just proved that X is regular, so we can take any point little a in my set A together with the entire closed set B and find disjoint open sets U sub A containing A and V sub A containing set B. And just like before, the collection of all of the U sub A's is an open cover for the set A, because every element A of A is contained in at least one of those. And really we're doing the same thing we did before, okay? So since A is a closed subset of a compact space, A is also compact, so we can find a finite subcover of our cover up here, UA1 through UAM. And just like before, we're going to let U be the union of these guys, and V is going to be the intersection of the corresponding VAIs. And it's a finite union, finite intersection of open sets means U and V are both open, and A is in U because these are a cover of A, and B is in V because B is in every single one of these sets, so it's in the intersection as well. Okay. And we want to show that U and V are disjoint. If we had an element in the intersection, then, well, it has to be in some UAJ, and it's in all the VAJ, so it's in the corresponding VAJ in particular. But if it's in both of those, then well, the intersection of those two is the empty set by sort of construction up here. These are assumed to be disjoint, and so we don't have any elements in U intersect V, and the intersection is empty, so U and V are disjoint, proving that X is normal. Now, if you want an example of a topological space which is, let's say, normal but not, Hausdorff but not normal, right? Well, then you know it can't be compact, right, or it would violate this theorem. If you want to see an example of that, you can Google the half-disk topology, and there should be a Wikipedia page that'll show you how that's defined.